Okay, so first we're going to look at C1. So C has to do with the work kinetic energy theorem. So it says a student wearing frictionless inline skates, so we're doing C1, on a horizontal surface is pushed by a friend with a constant force of 45 newtons. So before I go on, in my given, I'm going to write that F is equal to 45 newtons. How far? So how far? How far?
Pretty far.
I am not going to keep reading. I'm going to say, what do I want to find in this problem? I want to solve for D. Must the student be pushed starting from rest? Does that mean something? Yes. So VI is 0 because I start from rest. So that her final kinetic energy, so this is going to be KEF, is equal to 352 joules. So where do I start? Well, when you don't know where to start, you go to the end. I want to find D. Now, let me tell you something really great about these practice problems. The practice problems in your textbook, they're all grouped where they all use the same equation. And that's why we practice these first before we do the ones that are mixed up and we have to figure it out. So this, we're going to be using the work kinetic energy theorem. So work is equal to the change in kinetic energy. Now you might look at that and say, I don't get it. I have F and I have D. Well, that's with what we learned yesterday. Yesterday we learned that work is equal to FD. So FD is equal to the change in kinetic energy. So FD would be equal to KEF minus KEI. Now, would I memorize the equation like this? What I would do is I would probably memorize the equation like this, but I still need to know what I learned yesterday, that work is equal to FD. And delta KE is KEF minus KEI. Now, what if I was given the mass and the velocity? Then I could then break it up again, but I'm not given that in this particular problem. So in this particular problem, I want to solve for D. So at this point, I would rearrange the equation to solve for the unknown in terms of the known. So I'm just going to divide everything by F. That's it. So I'm going to say KEF minus KEI over F is equal to D. So now I'm going to substitute in my value. So KEF is 352 joules minus, if it starts from rest, does that mean something? Remember that kinetic energy, so KEI is 1/2 mVI squared. So if VI is 0, the whole thing is 0, isn't it? So it's going to be 352 minus 0 divided by 45 newtons. Now when I look at the math part of it, so I take my calculator and I do the math part of it, I have 352 divided by 45, and that comes out to be 7.8. And I know D is supposed to be meters, but you know what? I'm not sure. Maybe I made an algebra mistake. So that's the great thing about physics, is we have a foolproof way to check our work every time. Now, you don't have to write it all out like I do when I show you, but you can just do it in your work. So I have joules in the numerator divided by a newton. And I know a joule is a newton times a meter. So a newton times a meter divided by a newton, that's an easy one. It's a meter, and that's the correct unit. So I know I didn't make a mistake. So if we have a foolproof way to check our work every time, we should probably do it. So that's C1. So what do we need to know there? We needed to know that work was equal to the change in kinetic energy. We need to know work is equal to FD. And delta, the change in kinetic energy, is always going to be the final minus the initial. Now, I'm just going to set up number 3 for you, okay? And then you can do the math part, the part with the numbers. All right, number 3 says a 40-kilogram child. So we're given the mass is equal to 40 kilograms. Oh, I'm looking at the wrong problem, sorry. So I'm given the mass of a car is 2.1 times 10 to the 3 kilograms. It starts from rest, VI is 0, at the top of a driveway that is sloped 20 degrees. Oh no, this is like the last chapter. I thought we were done with all that. No. With the horizontal, an average friction force is equal to 4.0 times 10 to the 3 newtons impedes the car's motion, so the car's speed at the bottom of the driveway is 3.8. I think you're already trying to get a feel for this problem. What is the length of the driveway? Now, in this particular problem, again, the first thing we're going to do is, guess what? We're going to draw a free body diagram. Now, which way is the car moving? The car is moving down the driveway, so I'm going to make down positive, and then perpendicular to it is going to be my other sign convention. I always want my sign convention to go in the direction in which an object is moving. So when I sum my forces, so now, what's going on here? Well, there's friction, so remember, if the object is moving this way, friction always goes opposite the direction of motion. So I know my frictional force is going this way. I know my weight always acts straight down. And I also know that my normal force always acts perpendicular to the surfaces in contact. So this is my free body diagram, and I know that this is 20 degrees. Now, the thing is, before I can start, and that you guys are like, why are you doing all this? Okay? Why am I doing all this? Because what's going to happen is, I know work is equal to the change in kinetic energy. This problem has to do with what? What does this problem have to do with? This is in the section in the book, and this is where we practice. That's why they're called practice problems, where work is equal to the change in kinetic energy. So let's just jump to that step so I know what I need to do in this problem. So I know that work is equal to delta KE. I know work is equal to FD, which is equal to KEF minus KEI. Now this work, like I showed you yesterday, this can be the net work. We want to solve for D. So on this particular problem, what we're going to do is we're going to say D is equal to KEF minus KEI over F net. Remember, and this is the direction in which D is going, and then we're going to have our problem solved. And what makes this difficult, and it makes it challenging, and something you have to think about is, we're going to have to do all that stuff we did in the last chapter in order to find F net. Because KEI, I can find, first of all, KEI is 0 because it starts from rest. So I can add that to my given that KEI is equal to 0. So what I'm going to end up doing is 1/2 mvf squared divided by F net is going to give me that distance. So what I really need to do is I need to do this. So that's what's the net force going in this direction that's causing this displacement. Step by step by step. All right, now what should we do? Well, what do we have to do? We can't sum forces until everything in this problem has to be either parallel or perpendicular to the surfaces in contact. So the only force that's not going in that direction is the weight. So we're going to redraw this, just like we did in the last chapter. And we are going to leave f of f alone. We're going to have my normal force, and instead of the weight, we're going to replace it with its components. Now, if I did in this little diagram like this, remember, they have to be parallel and perpendicular with that angle. So I'm going to replace this, and I'm going to call it FGY, and I'm going to call this FGX, because this is my sign convention, X and Y. And what I do, I always do it to the side. What I always do is I will draw my FG to the side, because when you do stuff in your head and you don't write it down, that's how you make a mistake. So if that's FG, remember the components, they have to be added head to tail. They're perpendicular. This angle here is similar to that other angle. This is FGY and this is FGX. And if I have a right triangle and I know the hypotenuse, I can find the components. So FGY is equal to FG cosine of 20 degrees, which would be MG cosine of 20 degrees. Now you need to do that on your calculator later, but it comes out to be 19339. And I'm just writing this out, so when you go back tonight and do this, and you do it step by step in the calculator, you're going to write in yourself that intermediate step, where you're going to put an mg in the cosine of 20. The next one is FGX is equal to FG sine of theta, which would be mg sine of theta. Again, this is sine because it's opposite the given angle, and this is cosine because it's adjacent. And then you can work that out tonight, and that comes out to be 7,039. This is a challenging problem. Okay, this is the type of problem that's going to prepare you for college level physics. Would I necessarily put one of these on the test? No, this is a long problem to put on the test. Is it my responsibility to make sure you know how to do something like this? Yes. Because if I didn't teach you how to do this, you wouldn't be prepared for what you need to know. All right, so if we go back to the stuff that we did in the last chapter, remember, we want to end up solving for that F net, which is this way. So if I write it all out and I say this way is positive, summation of f of x is equal to ma. Now, what forces are going in this x direction? I look at my free body diagram. This is positive, so that's FGX. That's negative, so it's f of f minus, and that's equal to ma. So now, this MA is actually equal to what? That's actually F net. So I don't have to make this as hard. So once I figure this out, I have what F net is. So I don't even have to, I don't need the acceleration, I just need F net. So FGX was 7,039, and F of F did we figure out F of F?
It was given.
Oh, so that's it. So this problem really isn't that hard, because we don't have mu and all that other stuff. So once I figure out what this F net is, which should come out to be 3039, I just put it back in this equation. So this is just showing you how in physics, you don't forget everything we learned from chapter to chapter. Now we're learning new stuff. We're learning about work and kinetic energy and stuff like that, and we can relate it to the other things.
So what's KES then?
For practice D, 1 and 2 just have to do with plugging numbers in an equation, 1/2 kx squared. So you guys can do that on your own. The one that's challenging is number 3, and it's all about doing a diagram. One of the things I tell you over and over and over again is in physics, you need to conceptualize a problem, which means drawing a diagram. So let's look at number 3. So we're going to do D3. So it says a 40-kilogram child, so we're going to write our given, and that's the mass, is on a swing that's attached to a rope that's 2 meters long. So what is that 2 meters? Well, we'll do a picture, but that's going to end up being our height. Find the gravitational potential energy associated with the child relative to the child's lowest point in the following conditions. A, when the ropes are horizontal, B, when the rope makes an angle of 30 degrees, and C at the bottom. So you guys are probably like, what is that? What you need to do is you need to draw a picture. So we're going to start with the ground, which is first of all going to be our frame of reference, and this is going to be our lowest point. Once you actually see the picture, the problem's simple. So the child is on the swing. So this is at the lowest point, which is the third part, I think. That's part 3, right? That's part C. Then they ask us when it's at a certain angle, which is part B, and then they ask us when it's over here, which is part A. So this angle here is 30 degrees. So for part A, they say, what is the potential energy? Well, I know potential energy is equal to mgh. So it's equal to the mass, which is 40 kilograms, times gravity, which is 9.8 meters per second squared. And you notice I'm not putting the negative in because, you know, energy is a scalar quantity. So right now we're not concerned with, there's not going to be a direction, okay? And we can lose it, but right now we're just going to leave it like this because we don't want to get confused, times the height. So the height above the ground, if I have a swing and I swing it like this, what is this height actually above the ground? Isn't it just the length of that swing, the height? So that's going to be 2 meters. So when I multiply this on my calculator, the buttons I press, I'm just going to press 40 times 40 times 9.8 times 2, and it comes out to be 784. So the potential energy is 784 joules. So that's part A. Now for part B, you're going to have to use your knowledge of geometry, right? Because this is 2 meters, but what is my height above the ground? Do you see how this is the height I have to plug into the equation for part B? So this is why in physics some people find it challenging because you have to have very good math skills to be successful in physics. Because now when we look at this problem, we know that this height is 2. This is not 2. So what I would do is I would take this triangle. Isn't this a right triangle here? So I'll just draw that to the side and say at point B, again, here's my frame of reference. I know that this is 2 meters. And what I'm going to do is I need to find height. So what I'll do is, because this is a right triangle, this is 2 meters, right? I know that this angle here is 30 degrees, so I can find, let's call this H prime. So once I find this height, this is 2 meters, I find this because it's a right triangle, and then I subtract 2 from this, and that'll be my height above the ground to find the potential energy. So what makes this more challenging is your knowledge of geometry, right? Is this physics? Does this have anything to do with physics, finding what this height is? It has nothing to do with physics. It has to do with your math skills. We're not just plugging numbers in like part A. Now I have to apply my math skills to physics. So now my potential energy is equal to mgh. Should I be able to find what this height is? Yeah. If I can't do that, I'm not going to say. But anyway, how would I do this? Well, is this opposite? What's the relationship between this and this angle? It's adjacent. So adjacent is cosine of theta is adjacent over hypotenuse. So cosine of 30 is adjacent, h prime over the hypotenuse, which is 2. So h prime is equal to 2 meters times the cosine of 30 degrees. So now I put this in my calculator. Remember, for these calculators, I go from here to here. So I would say 30, then I would press cosine, and then times 2 equals, so it comes out to be 1.73. So that means that this height here is 1.73. So now when I use this equation, potential energy is mgh. It's 40 kilograms times 9.8 times, and the height would be 2 minus 1.73. Which is 0.27. So when I do that on my calculator, and I say 40 times 9.8 equals times 0.27, that comes out to be 105.84, so we'll say this is 106. And then the last part, part C, says what's the potential energy at the bottom, and the height is 0. So potential energy at the bottom is just 0. Now you could plug in all the numbers if you want, but if you know h is 0, why would you bother doing that? And that's it.